Excuse me, my keyboard and mouse stopped working for a while, and now I'm back. Where we stopped is for the next step. The next major step of iteration is to calculate the weight for the weak classifier according to its performance on the resample data. I will copy this part below here. Calculate the classifier weight. So as before, I'd rather call it error, and this is the error rate. Let's just call that error. So here, those AL representing alpha will be the weight for the classifier. Let's put a comment here. And as we said, both the internal parameters of the classifier, which is represented by this object, and the alpha, this weight, are part of the model parameters of eta boost. Therefore, we need to take a record of that. Let's say eta boost model. The model consists of two parts. I will use a dictionary to store the two parts of the model. Weights, which is an empty list, and weak predictors, which is also a list. So we use these two lists to store all the information of a trained eta boost model. Now we will store those two parts of information. Eta boost model. We use string to index the k as the k weights. This is a list, and a list we can append a value to the list, which is IL, and eta boost model, the weak predictors. This will be appended by the trained weak classifier G. And in the next, we will reweight the samples. For the next step, resampling. The samples, the adjustment of the sample weights are calculated in this way. Remember this shift by minus 0.5 and times by 2 represent the converting whether the error record into -1 to +1. So the resampling and this is resampling, and this is to normalize the sample so that they sum to 1. Therefore, it can be used in the resample of the index as here. Okay. Excuse me. So basically, that is what we want. Of course, we will need a stop condition. We don't want to stuck here forever. Let's do a simple straightforward one. We stop after 5 times. Okay. Let's see. Max iter 5, iter number is 0. Okay, stop condition. Now let us to increase the iteration number, and now we have done once, and second time this will be the iter number will be 2, so on and so forth. If iter number equal greater than max iter, then we'll take a break. So that is the simplest AdaBoost implementation. I'd rather to recreate everything to start over. Okay, and then now let us do this construction of AdaBoost and see what happened. I'd rather to print some information along the way. Print, maybe we can see what iteration. In this iteration, let's say the prediction of resampled, maybe. Print x. We do not need this. Later. X resampled we do not need to unnecessarily need to print out the y for every time, but we can look at the error, which is a, and we also have a look at the alpha. Wait. Okay, last, let's have a look at the weight of the samples. Weight. Exactly. Okay. Uh-oh. We forgot a comma here. So let's go. Now it runs. In the first round, it goes this way and has an error of 0.3, and in the second time it goes this way, so on and so forth. Let us see. Lastly, it goes this way. We may want to check how AdaBoost as an ensemble works on the data. So to do that, let us create how that works. Say if we have an AdaBoost sample model, as we have done here. So now this has a family of weight classifiers and corresponding weights. Okay. Now let us do the prediction according to this family. For weights and predictors in, we will zip the two parts together. Okay, this is weights, classifier weights is yes, weights, and the corresponding classifiers. Let us use these to use the classifier to predict x. So let's check its performance on the x. Okay, and the total prediction numpy zeros like, well, this is a convenient way of create a similar object of the same shape but are all zeros. I think I will need to specify the data type to be float because I don't want it to be integer, otherwise I cannot accumulate the weighted predictions. Total predict accumulating a times prediction. Okay, lastly, let's print out the total predict. See how that works. It seems that now the predictors are going to the right direction, but it needs some final adjustment. Look, for all the middle values where we wanted to predict -1, it predicts smaller values. And for those values with the desired target are positive one, it predicts larger values. But now, for now, all the values are still above 0. Let's see if we let the ADA boost run for more times, what will happen? I have set the iteration to be 10. Well, lastly, I got a very small error. Here I have an error 0.0, but there is an problem, numerical problem here. That is because the calculation of divide by 0 creates a problem. So to avoid those numerical difficulties, let us adjust this a little bit. That error could be maximum. So now we forcefully set the error to be minimal as 1 millionth. This is an artifact, but it's useful, numerically useful. I'd like to reset the random generator and the sample width in the beginning of this training set, which facilitates our adjustment, our debugging of the algorithm. Now we do not need to go up and initialize the algorithm over and over again. Do that again. Now, what we have here? Well, it seems that we have made a small bug here. I accidentally introduced the bug here when I introduced the technique of keeping the errors. When we do the reweighting of the samples, instead of using the error record we have computed on the resampled training samples in this round, we need to reweight the original samples using the trained predictor's prediction on the original samples. We should do this rather than evaluate on the resampled set. Now, those GW tend to be correct, and let's see how this algorithm performed in this way. Okay, still has some errors. Let's do 15 times. Now, it seems that this algorithm has now performed very well on the training set. We can have a look at its behavior on the training sample using visualizing it. Import matplotlib.pyplt and plot. Let's compare x with the total prediction. Let's overlay that with the y. So this is AdaBoost prediction. Of course, because eventually we will choose a side according to the sign of the predictor's value. So these are all correctly predicted as positive classes, and those are negative classes. It seems that still has an error here, but let's see if it can. It does not make much sense if we insist that a classifier must make 0 errors on the training sample. But just for example, let's see. Okay. Now the sign of the predict value agrees totally with the training targets. NumPy.sign. This will give the positive or negative. I will adjust its value a little bit so that we can check the difference on the graph. Okay, that's a predicted value, a predicted class, and this is the training class. So that is a sample demonstration of implementing with experience of debugging a little bit the algorithm of AdaBoost and use AdaBoost ensemble to do predictions and check prediction on the training set. Of course, when you want to apply the model to raw data analysis problems, you will have to split the training rather than this toy sample, for which we only have 10 samples. In practical problems, you need to split in the data into training and validation set and train your model, ensemble model on the training set and evaluate its performance on the withheld validation set. That applies to all data models, including the ensemble models here.